Hello there, welcome to CXC Math TV. Today we will be looking at arguments and modulus of complex numbers. Really nice. So you might be wondering, what is the modulus of a complex number? What is this argument of a complex number, right? Argument, really? Argument? Yes, argument of a complex number. Now, before we can find the modulus and argument of a complex number, we first need to talk about what is known as a Argon diagram. Now you're going to ask, what is an Argon diagram? What is this Argon diagram? Why are we learning so much stuff? No worries. Now consider this complex number, z equal to 1 plus I. Now if you have the complex number z equal 1 plus I, we would say that the real part of the complex number is 1 and the imaginary part of the complex number is also 1. Noted. Now the Argon diagram is pretty much a graph for how we are going to draw complex numbers. Yes, in the same way we can draw graphs for real numbers, we can draw graphs for complex numbers. The horizontal axis is known as the real axis and the vertical axis is known as the imaginary axis. And so the complex number z equal 1 plus I, right? We can write that as a point. As a point, the real part is 1 and the imaginary part is 1. So on the Argon diagram, we're going to just draw from the origin of the graph to the point 1, 1. We're just going to draw a straight line. That straight line represents the complex number z equal to 1 plus I. And all you then do is label your axis. The y-axis is the imaginary axis. So we write Im in bracket z, meaning the imaginary part of the complex number, and rez means the real part of the complex number. So go ahead and pause the video and attempt this question. Draw the Argon diagram for minus 5 plus 12i. As you should have paused the video and attempted, we'd have seen that the real part is negative 5 and the imaginary part is 12. So all we do is put that as a point, negative 5, 12, and then we draw a straight line from the origin up to minus 5, 12. Hey! And so that would be the Argon diagram of the complex number, negative 5 plus 12i. Beautiful. So go ahead and plot the following Argon diagrams for homework, minus 3 minus 4i, and minus 20 plus 20i. You can attempt that for homework. So this is what you should have gotten for the first one. You're in the third quadrant. And for the next one, minus 20 plus 20i, this is what you should have gotten. You're in the second quadrant. Beautiful. Now, we can go back to the argument before. You see what I just did there? I said argument. We were talking about the modulus and the argument of complex numbers. So you're wondering, what is this modulus? What is this argument? Now, the modulus of a complex number is just the length or the magnitude of the complex number. So let's consider z equal to a plus bi. In order to find the length of the complex number, the length of the complex number is just going to be the square root of the real part square plus the imaginary part square. So anytime you're given a complex number a plus bi, to find the magnitude, it is a square plus b square square rooted. And that's going to give you the length of the complex number as we depict on the graph right here. So, for example, find the modulus of the complex number 1 minus 2i. To find the modulus of the complex number 1 minus 2i, the real part is 1, the imaginary part is negative 2. So the modulus is the square of the real part, 1 square, plus the square of the imaginary part, negative 2 square, all square rooted. And so that is 1 plus 4 square rooted. 1 plus 4 is 5. So we say that the modulus is the square root of 5. Please remember, modulus means length. Modulus means length. Cool. So look at this now. So find the modulus of the complex number 1 minus 2i. We did that and we got the square root of 5. So if you were to draw the complex number 1 minus 2i, that's in the fourth quadrant. All we're saying then is that the length of the line that we drew from the origin up to the point 1, negative 2, the length of that line is the square root of 5 units. That's all we're saying. That's the length of the line. So go ahead and attempt these for homework. Or you can pause and attempt right now. Minus 15 plus 8i, find the modulus of that. 4 minus I, find the modulus as well. And 1 plus I, find the modulus. As you should have attempted, you should have gotten 17 units for the first one, as displayed the solution on the screen here. For the second one, we should have gotten root 17 units. And for the third one, we should have gotten root 2 units. Alright? Lovely. So now we're going to start talking about arguments. So you might ask yourself, arguments, what is this argument? The argument of a complex number is the angle a complex number makes with the positive real axis. The positive real axis? Yes, the positive real axis. Only focus on the x-axis in the first quadrant. So every other part of the x-axis you can ignore. The x-axis in the second quadrant, ignore that side. Because we only focus on the angle that a complex number make between the positive real axis and the complex number. Alright, as displayed by the diagram here, that would be that angle in there. So, arguments depends on the quadrant. That is something that we need to know. Argument depends on the quadrant. Why does it depend on the quadrant? Now, the argument depends on the quadrant because there is no set way of finding the argument for all quadrants. Because if we're in the first quadrant, the angle is going to be between 0 and 90. In the second quadrant, it might be in a different range. So in the case you're in the first quadrant, alright, the argument can be found by tan inverse of the imaginary part over the real part. That's if you're in the first quadrant. Alright, because in the first quadrant, the complex number and the real axis, the angle is going to be between 0 and 90 as displayed by the diagram. So let's say we want to find the argument of 1 plus I. So the argument of z is going to be tan inverse of the imaginary part, which is 1, over the real part, which is 1, and tan inverse of 1 is pi by 4. Remember, keep a calculator in radians. So since the argument is pi by 4, we can definitely see, if we draw the Argon diagram right there, that look at that. Right? That's the angle between the complex number and the real axis, the positive real axis, is pi by 4. Nice. So now, how do we find the argument of a complex number in the second quadrant? Now, to find the argument of a complex number in the second quadrant, let's put up a diagram to show how it would look. In the second quadrant, that is the positive real axis, and the complex number would be somewhere over there in the second quadrant. So the angle is going to be a little bit bigger. It's going to be an obtuse angle. So the argument of z is going to be between 90 degrees and 180. That's between pi by 2 and pi. So how are we going to find that angle? Well, if the complex number z is a plus bi, then the argument is going to be pi plus tan inverse of b over a. That is how we're going to find the argument in the second quadrant. And so let's do an example. Z is minus 1 plus root 3i. Find the argument. To find the argument of this complex number, we just need to remember the formula. It's pi plus tan inverse the imaginary part, which is root 3, divided by the real part of negative 1. So it's going to be pi minus tan inverse of root 3 over negative 1 is going to be minus pi by 3. Pi plus minus pi by 3 is just pi minus pi by 3, which works out to be 2 pi by 3. If you did it in degrees, it would have been 120 degrees. And so that is the angle right there, 2 pi by 3. So the argument of the complex number is 2 pi by 3. Beautiful. Now what about the third quadrant? The third quadrant and the positive x-axis, right? then the angle is going to be right there as displayed on the diagram. Now, how are we going to find that angle? In that case, we are going in the counterclockwise direction, because the angle between the positive x-axis and a complex number in the third quadrant, that's going in the opposite direction. So the angle is going to be negative. And so the formula that we use then is minus pi plus tan inverse b over a. Let's look at an example. Let's say we have the complex number minus 2 minus 5i. So the argument is going to be minus pi plus tan inverse of the imaginary part negative 5 over the real part of negative 2. That's going to be negative pi plus 1.19 radians, because tan inverse of negative 5 over negative 2 is 1.19. That works out to be negative 1.95. So therefore the argument is negative 1.95 radians. Notice it's negative because we're going in the counterclockwise direction. Nice. Once you're below the positive real axis, the angle is negative. Let's say that one more time. Once you're below the positive x-axis, the angle is negative. Let's look at the fourth case. In the fourth case now, in the fourth quadrant, how are we going to find that angle? We know it's negative. Now, to find the angle in the fourth quadrant is the same formula as the angle in the first quadrant. It's just tan inverse of b over a. Isn't that beautiful? Just tan inverse b over a. So let's say you have the complex number 1 minus I. The argument is just going to be tan inverse of the imaginary part of negative 1 over the real part of 1. That's negative pi by 4. So the angle is just minus pi by 4. That is the angle right there. So you draw the complex number 1 minus I, and the angle between the positive real axis in this case is just negative pi by 4. Beautiful. So pause the video and attempt these questions. Find the modulus and the argument of the complex number z equal 2 minus I over 1 plus 2i, and find the modulus of the roots of the complex number z squared minus 4z plus 5 equal to 0. Pause and attempt. Now, with the first one, first thing we have to do is multiply by the conjugate of the denominator, because that complex number is not in its standard form. We always want to put it in its standard form. So we multiply by the conjugate of the denominator, and when we simplify the numerator, we're getting 2 minus 4i minus I plus 2i squared. And we simplify the denominator, that's the difference of 2 squared. Now in the numerator, I squared is minus 1. So that becomes 2 times minus 1, which is minus 2 right there. And 2 minus 2 is 0. Minus 4i minus I is minus 5i. And so this works out to be minus 5i over 5. Now we'll do the division, that's just negative I. Now the real part is 0. And so the magnitude of this complex number, or its modulus, is 0 squared plus negative 1 squared square rooted. And so that have a magnitude of 1. Now what about the argument? Now the argument is tan inverse of negative 1 over 0. What is tan inverse of negative 1 over 0? No, that is undefined. We don't know tan inverse of negative 1 over 0, so that's undefined. Alright? So the modulus is 1 and the argument is undefined in this case. Now, let's have a look at question 2. We were asked to find the modulus of the roots of the complex equation z squared minus 4z plus 5 equals 0. So first we need to solve the equation for the roots. So we use the quadratic formula. So it's minus b, so it's going to be negative 4, which is positive 4, plus or minus the square root of b squared, that's 4 squared, minus 4 times 1 times 5, divided by 2. So we put that in our calculator, and we get 4 plus or minus the square root of negative 4 over 2. But the square root of negative 4, we can break that up as the square root of 4 times the square root of negative 1. And the square root of 4 is 2. The square root of negative 1 is I. So we end up get z is, when we divide the numerator and the denominator by 2, we get 2 plus or minus I. And so the magnitude is going to be 2 square plus 1 square, because it doesn't matter if it's negative 1 or 1. Because once you square negative 1 or 1, you're going to get 1. So the magnitude is just the square root of 5 units. And that is it. Nice. So first thing we need to remember is that if you're given a complex number z equal a plus bi, then the magnitude of z is just a squared plus b squared all square rooted, and the argument of z is just dependent on the quadrant. We must remember that. So that's it from CXC Math TV. Stay tuned for more. Alright, stay tuned for more as we have lots of wonderful topics coming soon. Take care and make sure you have a blessed day.